This is part 5 of 8 in the Black Road Sky version 0.3 video tutorial series. In this video, we'll be learning the basics of orbital mechanics, specifically as they apply to playing Black Road Sky. It's not exactly rocket science, but kind of it is. That was annoying. That was an annoying thing to say. So I'm going to start by saying that there are much better ways to learn orbital mechanics than by watching this video. But you also don't need to be an expert to get by in Black Road Sky. I certainly am not. So I'm just going to try to give you the basic tools that you need to keep playing this game once you run out of contracts between Gagarin and Laika. So we won't actually be making any progress in the game here, so you don't necessarily need to follow along, but wouldn't hurt, I don't think. This is going to be, I expect this to be a long, rambling video, so don't forget to grab a beverage to make your head hurt a little less, at least until tomorrow morning. All right, let's start out by going over the orbital data that's displayed on the left-hand monitor here. The first line, SOI, means sphere of influence. This indicates the body whose gravitational influence you are most affected by. In fact, just peek behind the curtain, it's the body whose gravity you are being affected by, period. Not most. It's a two-body orbital simulation. You know, but this tells you what planet you're in orbit around, basically. G, that's gravity, the acceleration due to gravity being experienced by your ship at this point. It's not actually super useful navigational information, but it's sometimes good to know. Altitude is an important one because when that's 0, you've crashed. It's good to know how high you are above the planet, and this is altitude above the surface of the planet. If that's not obvious, rather than distance from the planet, which would be calculated from the center. And I think maybe it's some other place in the UI is calculated that way. Apo is apoapsis. This is the highest point in your current orbit. And peri is periapsis. That's the lowest point in your current orbit. So you can see from that we are currently at the lowest point in our orbit. As we travel in our orbit around Tyra, our altitude will raise to 456.94 kilometers at our apoapsis, and then on the other side of our orbit, lower back down to 404.70. These are really important values, which we'll be talking a lot more about throughout this video. Eccentricity, that's the ECC, is the next value. This is essentially how circular your orbit is. An eccentricity of 0 is a perfectly circular orbit, so as you can see, we're pretty darn close at the moment. Anything between 0 and 1 is an elliptical, closed elliptical orbit. Exactly 1 is a perfect parabola, and anything greater than 1 is a hyperbolic orbit. In other words, an escape trajectory from the planet. So the important number to remember with eccentricity is 1. If you're less than 1, you're in orbit. The closer to 0 you are, the more circular that orbit is. Below that is inclination. Inclination is sort of the tilt of your orbit. 0 degrees is a prograde equatorial orbit. 90 degrees is a polar orbit. 180 degrees looks the same as 0 degrees, but it's in the opposite direction. Inclination isn't a huge worry most of the time in this game. All of the planets and moons and space stations are in pretty low eccentricity, low inclination orbits. So you're never, at least yet, in this version of the game, you won't experience a situation where you need to put yourself into a polar orbit, but you might find yourself in a situation where you are in a polar orbit by mistake. So if you see an inclination of 90 degrees, that's what that would mean. T is why is it called T? I'm not sure where the letter comes from, but that was someone else's idea, not mine. That's your period. In other words, how long it takes you to make one complete orbit. In our case right now, 1.55 hours. And then finally, velocity here under the orbital data is different, obviously, than your velocity here. This is our velocity relative to Laika orbital. This is our velocity relative to the planet that we're orbiting. Laika orbital is also moving around the planet, so there's no such thing as a absolute velocity. Every velocity in, I mean, not just in the game, but in life, in reality, is velocity only makes sense relative to another object. So this velocity under the orbital data heading is our velocity relative to the planet. Actually, again, much like gravity, not super navigationally useful. It's just there because, I don't know, I think it's kind of interesting. It could be useful, I guess, in some situations. So we can use this data to visualize our orbit and sort of imagine what it looks like in our head if we know what all of these numbers mean, but that's obviously not very convenient or easy to do. So what we can do is to bring up the map display with the map button. Note that the map and sensor displays cannot be up at the same time because they occupy the same area of the view screen. So if you happen to have your sensors up already, you have to kill them in order to bring up the map screen here. The map has two modes. We're currently in system mode, which is just basically a map of the solar system. And you can click on icons to get more information about certain planetary bodies. This planet happens to have 4 moons. I can click on one of the moons to get way more information than I want about it. And I can also set celestial bodies as targets for the readouts over here. That's but system mode is basically just it's just a map. We can hit this button in the corner to switch from system mode to orbital mode. In orbital mode, here we see Tyra represented as this solid white circle. Our ship is the orange triangle, which is currently hiding a little bit under the icon for our currently selected target, which is like an orbital, of course. And this thin line traced around the planet is our current orbit. So we'll keep this display up as we continue here so that we can see how various thrust maneuvers that we make affect our orbit in real time. Let's start by raising the altitude of our orbit. That's a pretty common maneuver that you'll want to make. So start by looking for this symbol. on your nav ball. This is our prograde direction. In other words, the direction that we are currently moving in. So remember, no air resistance in space. You're often in a situation where the direction that you're moving is not the direction that the nose of your ship is pointing. So aligning the nose of your ship with this icon on the nav ball means that you are now pointing exactly in the direction of your motion. It's a little bit hard to see because Leica orbital is in our way, but if you look at our the triangle here representing our ship, you can see that we are in a counterclockwise orbit as it's displayed on the map screen, and this is the standard orbital direction. Every planet, moon, and space station in Black Road Sky, at least in the version that we're playing right now, is orbiting in this way, counterclockwise when viewed from the map screen, which is, by the way, viewing from above. So this is the North Pole of the planet right here, and we're looking down at it, orbiting counterclockwise. Useful fact to keep in mind that everything is orbiting that way. So with the ship pointing prograde as it is, we've drifted a tad. Point myself directly prograde. I'm going to throttle up a bit, and we'll just see what happens. Perhaps what's happening is clear here, but if not, what we've done is raised the altitude of the opposite side of our orbit. Now this line left behind, this is Leica Orbital's orbit. Leica Orbital's orbit. When you select a target, you get its location as well as a visualization of its orbit. And you know what I'm going to do? Rather than constantly complaining about how Leica Orbital's in the way, I'm going to go back to the sensor screen and hit clear. And that cleans things up a bit. Well, it's supposed to clean things up a bit. That's a bug. All right, that square is not supposed to be there. But we at least don't see Leica's orbit. All right, busted. So if I were interested in raising my apoapsis to a specific altitude, then as I'm throttling up, I can keep an eye on my apoapsis here. I'm going to throttle up again, and you can just see it go up and up and up and up. So our orbit is now going to take us nearly 7,000 kilometers away from the planet. Our orbital period has increased dually, and we can see the shape of our orbit here on the orbital map. Now, if I want to circularize my orbit at this new altitude of 6,800 some kilometers, what I want to do is now raise my periapsis, which is again the lowest point in my orbit, where I am now essentially. I want to raise that altitude to match my apoapsis. That would be a circular orbit. So with my current orbital period of 3-ish hours, I could just wait a little less than an hour and a half for my ship to go over there. I could just walk away, make a sandwich, watch some Gilmore Girls, some Dawson's Creek, depending on your politics. But I'm not going to do that. Instead, what I'm going to do is get out of the pilot seat and introduce to you the cryopod. The cryopod is just a way to accelerate time. I wanted something in fiction rather than just a button that you press to make things speed up. Using the cryopod is straightforward. You enter it and you hit the button. Use of cryopod is prohibited within 100 kilometers of any station, or when you're throttled up at all. If your boosters are throttled up, or if you're within 100 kilometers of a station, you won't be able to use the cryopod. So if it's not working, you probably are in violation of one of those conditions. So here we have access to the map screen, and I can flip her into orbital mode there. And what I want to do is get myself here-ish. I want to get myself to apoapsis, so let's go ahead and increase time. Being careful not to overshoot. Now notice, as I get farther away from the station, I also slow down. It may have been hard to see there, but it's true. As I get farther away from the planet, rather, the farther away I get from the planet, the slower I'm going to move. This is sort of a basic property of orbits. The higher the altitude, the slower you're going to move. So if you're trying to catch up to a space station that's in front of you, you want to put yourself in a lower orbit, and you'll gradually catch up to it. If you want a station that's behind you to catch up to you, you put yourself in a slightly higher orbit and let it catch up to you. This is something that most people find somewhat counterintuitive. So like, I blasted straight ahead to raise my apoapsis, and now I'm going to blast straight ahead again to raise my periapsis. And the result of blasting straight ahead twice will be to lower my orbital velocity. Feels weird, but it's true. And if you want to learn more about it, you Google that shit, man. So what I'm going to do now is wake myself up here out of the cryopod, hit the button, open the door, and we're in all sorts of funky shape here. And what I'll do, I'm going to roll myself back around just to get my bearings, and then yaw back towards my prograde vector, taking the beautiful view of the suspiciously familiar looking planet Tyra. Get ourselves to prograde. And throttle up. You can see our periapsis raising there. We can see our periapsis raising there. We can see our eccentricity getting closer and closer to 0. And that's usually what I look at. I'll slow down a bit so I don't overshoot, and I'll just get my eccentricity as close to 0 as I can. That looks like about as close as it's going to get. Don't obsess about getting your eccentricity to 0.000. That's a damn nice circular orbit, if you ask me. Same with inclination. Close to 0 is good. Now, in the same way, we can lower our orbital altitude by firing retrograde. And retrograde is the direction, our ship's retrograde velocity, I should say, is denoted by this symbol. So just for kicks, I'll go ahead and do it. I'll burn retrograde, and we can see the altitude of the opposite side of my orbit lowered. So these basic maneuvers, burning prograde to raise the opposite side of your orbit and burning retrograde to lower it, are the most important orbital maneuvers to remember. There are always many different ways to accomplish an orbital maneuver, and these won't always be the most efficient, but they're enough to get you through most situations. That said, let's go ahead and take a look at the other nav ball directions and see how burning in those directions affects our orbit. So we're getting into more advanced territory here, and if you feel lost, it's probably because I'm doing a bad job of explaining things and because I'm slamming a cobra. So don't feel bad. Alright, let's give this a whirl. The red symbols on your nav ball, there's one here, and there's one on the exact opposite side of the nav ball. These are your radial in and radial out vectors. I've been trying to keep things simple. I don't think I've used the word vector yet, even though I've wanted to. I've used the word velocity when I should have used the word vector, because I've been trying to make things less complicated. If you the word basically vector and velocity, you can if you don't know the difference, you can think of them as being basically. But I'm going to use them basically interchangeably. So these markers are always 90 degrees on the nav ball. They're always going to be 90 degrees away from your prograde and retrograde velocities. They all move together. They all affect each other. Radial in is this symbol here. This points basically into your orbit, while radial out, which is this symbol, points out or away from your orbit. That's not exactly true, but but essentially, radial in, if you're in a stable orbit, radial in, where I'm pointing right now, is pointing straight into the planet. Radial out is exactly 180 degrees away, pointing straight out. If you're not in orbit around a planet, they can mean slightly different things. But I always think of radial in as towards the planet, radial out as away from the planet. And indeed, you can see here that is the case. So burning radially sort of rotates your orbit, and I know I'm going to do a bad job of explaining this, so let me demonstrate some practical applications, like why would I ever want to burn radially? Here are a couple common situations. So I'll go ahead and hop in the cryopod, and I'll put myself somewhere between apoapsis and periapsis. How about there? What the hey? And we'll hop back out. Run over to the pilot seat. And let's say that from here, I want to circularize my orbit. Let's say I hadn't just hopped in that cryopod, I just happened to be at this point in my orbit and I want to circularize it. Circularizing your orbit is often a useful first step in making an orbital rendezvous. And we know how to do that by burning prograde, waiting half an orbit, and burning again. But what if you're in a hurry and you have a contract deadline coming up and you don't want to waste time in the cryopod? And so instead of making one burn, we can make two burns from our current position, like so. So the first thing that I'll do is take a look at my altitude. If it's increasing, that means I'm moving towards my apoapsis, which means that I'll want to burn radially inward. If it's decreasing, I'm moving towards my periapsis and I'll want to burn radially outward. So a couple things to note before I do this. I'm going to apply a very small amount of throttle at first because this shit's confusing. I often get it exactly wrong. So I usually don't make big moves until I'm sure I've got it right, or until I've taken the time to think about it beforehand, which I usually just don't. The second thing to note is that burning radially sort of changes what radially means. Burning radially will change the direction of our radial vector. Unlike when we burned prograde or retrograde, we can just sort of hold steady. When we burn radially inward or outward, it's going to change the direction of those markers, and we'll have to use some attitude control to keep our nose on the marker. So, okay, my altitude is decreasing, so I want to be pointed radially outward, like so. And just steady myself in the center of that marker there. We'll point that way and apply just a little bit of throttle in a moment. But what before I do that, what I'm looking for, I want to see my periapsis increase while my apoapsis decreases. In other words, I'll be making my orbit more circular. So I'll give it a little bit of throttle and see if that's indeed what's happening. It is, so I got it right. And I can increase the throttle here, and I'll keep burning this way until either my apoapsis or periapsis reaches my current altitude. And you can sort of see slowly. I'll throttle up a bit. Here we see my, it's drifting away, so I'm going to apply a little bit of yaw there to keep up with it. You can see it's a bit subtle, my orbit rotating around, and pretty soon it looks like my apoapsis reached my periapsis, and in this case, honestly, that's as circular as you need to be. That worked out maybe a little too well to be an example. I should have had a bit of a bit more eccentricity going into that to give you to give a better example. But at this point, my altitude and my apoapsis match. I'm at my apoapsis now. I guess that's the point I'm trying to make, is that instead of cryopodding myself to the apoapsis, I put myself, I changed the shape of my orbit so that I'm at the apoapsis. And now, no matter what this periapsis was, it could be an impact trajectory. It could be, 20,000 kilometers. From this point, all I have to do is burn either prograde or retrograde, to adjust the opposite side of my orbit. And I could do that. Obviously here I could burn prograde to raise it a tiny bit to get that eccentricity. I mean, what the hey, we're here, right? Let's yaw around, have a drink while we wait. See how close to zero we can get that eccentricity. Throw just a tiny bit, and I'm not even looking at my periapsis here. I'm just looking at the eccentricity. 6, 5, 4, 5. Oh, that's as close. Overshot just a tiny bit. But especially when your inclination is low, under a degree or two, if it looks circular on this screen, it's pretty circular. It's good enough for our purposes. My intention is that you have to have some understanding of orbital mechanics to play the game, but that you don't have to be super precise. You don't have to be. The ship is powerful and efficient enough to brute force a lot of things. In fact, throughout all of these tutorials, I'm being much more careful than I need to be because I want to conserve fuel, because fuel costs money, and we're trying to get out of debt, remember? That's the game. So here's another situation where burning radially can be useful. I'm going to zoom out here. Oh no, that's another bug. That's probably the same bug. We'll ignore that square there. I'm going to flip into boost mode here, throttle up, and really blow my orbit out. That was too much. That was too much. Instead of spinning all the way around, I'm just going to go into maneuver mode there and put on my thrust deflectors to bring it back. Okay. I've zoomed out, if that wasn't clear. So this is the moon that I can see over there somewhere. There it is. That's Lua, the single moon of Tyra. So my orbit is now stretching way out to meet the orbit of this moon. And let's just say, for the sake of example, that the moon was somewhere in this vicinity. Commonly, if you're traveling from a planet to its moon, this is what you'll do. You'll extend your orbit out to reach it, and unless if you're really, really careful, you often miss the mark. But we can burn radially inward or outward to rotate our orbit and fix any little errors that we make there. So I'm going to throttle up a bit. And apply a little bit of yaw to try and stay on that marker. And you can see my orbit rotating along there clockwise. Especially in a high eccentricity orbit like this, you can see here's my apoapsis is really increasing. Your apoapsis will increase or decrease based on whether you're pointing a little bit closer to prograde or a little bit closer to retrograde. So now I'm adjusting that by pointing a little bit closer to retrograde, and then I'll swing back in here. And we'll try and stay right in the middle of that marker. And as I do, my orbit continues to swing clockwise. I'll throttle down, and I can, in the same way, swing myself back around burn radially inward to rotate my orbit in the opposite direction. This is useful not just for traveling from a planet to its moon. Often, when you arrive at a planet, you'll be in whatever orbit you end up in. You won't probably be thinking too hard about what the orbit of the space station that you're ultimately traveling to is in, and it's very, very often convenient to rotate your orbit in order to intersect the orbit of your target. I'll just for the sake of example here, throttle up here, and I can start moving my orbit around in the opposite direction. I'm watching both the nav ball and the graphical readout of the orbit. You could do it also by watching the numerical readout. I find that much less intuitive personally, but to each their own, huh? Okay, so that's 4 of the 6 nav ball markers. We're almost done. The last 2 symbols are these 2 green markers, these green triangles, which represent our normal and anti-normal directions. These are orthogonal or perpendicular to both the prograde, retrograde, and radially in, radial out. The third dimension is the normal, anti-normal. If the prograde, retrograde, normal, or prograde, retrograde, radial in, radial out lines sort of form a plane, that's making it more confusing, not less, isn't it? The a normal and anti-normal are orthogonal to those. That doesn't. You don't need to. Sorry, you don't need to know that. Okay. So if you're in a standard orbit, those markers will usually be on the top and bottom of the nav ball. In other words, facing quote unquote up or down relative to your orbital plane. You can tell from, I don't know if that helps or not. The main reason that you'll want to burn normal or anti-normal is to adjust the inclination of your orbit, which we've talked a little bit about already, but we will talk about more when we talk about making interplanetary transfers. Again, that's the inclination is sort of the tilt of the orbit. We covered that 90 degrees is a polar orbit, 180 degrees is a retrograde orbit. When your inclination is near zero, you're in a nice uh, equatorial prograde orbit. And we'll talk more about this later, but just for the sake of doing something here, you'll see if I burn, this is in the normal direction. Why they're called, oops, pushed the wrong button. Why they're called normal and anti-normal, I do not know. I guess normals are orthogonal. Anyway, it doesn't matter. But you can see when I throttle up, it my inclination starts to change pretty quickly. Worth keeping in mind, the view that you get here is a 2D from what I'm calling above view. So you're not getting all 3 dimensions worth of data. So you do have to kind of pay attention to the inclination results. Relative inclination is inclination relative to your current target, which um, we don't have right now, and yet it's still showing a number and a marker. That's a bug I need to fix. And inclination here is your inclination relative to your current, the body of your current sphere of influence. I'm not going to spend a ton of time here because it's not going to be a big concern until we tackle interplanetary transfers, since all the space stations in the game are on very low inclination orbits. They're all basically following the equator, so you shouldn't have to make major inclination changes just yet in your space trucking career, and we'll talk more about these kinds of maneuvers later on as needed. Okay, so I feel like that was a lot. I feel like a shitty drunk teacher who just gave too much homework or something. I encourage you to play around with these maneuvers, try to get comfortable with them, particularly raising and lowering your apoapsis, your periapsis, circularizing your orbit. Try to get an intuitive feel for how radial in and out works. Don't worry so much about normal, anti-normal yet. We'll dig more into that as we need it. And in the next video, we're going to be performing an orbital rendezvous with another station, probably with Canada City, the station that never sleeps. City stations have a slightly different layout and a different approach for docking that I want to cover. And we'll also be learning about the ship's warp drive, which makes these kinds of rendezvous maneuvers much easier than you may be used to if you're familiar with games like Kerbal Space Program or Orbiter or whatever. While they make rendezvous maneuvers easier, they do not absolve you of your responsibility in understanding orbital mechanics. You still need to be able to adjust your orbit appropriately, but you'll see why. We'll learn all about that in the next video. And until then, thanks for sticking with me through what basically amounted to a bad lecture on orbital mechanics. Catch you in the next one.